In this lab, two main softwares were used, known as Tracker, which we used to obtain motion data about our system, and glowscript to model our system to form predictions. Thus, the main purpose of this lab is to incorporate these softwares to form a comparison between how the position of our system varies with time in comparison to our model's predictions, while maintaining constant velocity to investigate the accuracy in our model's predictions. The results verify that our model is a good representation of our observations, but still has a few barriers that are different due to some errors. So in our experiment, the system is the ball, which we're going to be seeing later, and the surrounding is everything else, including the walls, bed, floor, and even earth. The main fundamental principles adopted in this lab are the principles of momentum, Newton's second law, Newton's first law, and the position update formula, which is what we are going to be going over. First, the momentum principle. It mainly discusses the easiness or difficulty that comes with changing the motion of an object, where the equation of momentum is P is equal to mass times velocity, which you can see on the screen. However, both of these variables remain constant, thus our momentum is actually constant. We can now link this information to Newton's second law. It explains how interactions between our system and the surrounding leads to changes in momentum. Its equation is actually displayed on the screen, and it shows that the total forces that are acting on our system is the change in momentum over time, dp over dt. And as mentioned previously, our momentum is constant, so the derivative of momentum, dp over dt, is 0, meaning our F net is 0. As we know, an F net of 0 signifies that we are moving at a constant velocity with time, and we can now relate this to Newton's first law, which states an object at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted on by a net external force. So this re-shows how an F net of 0 still means the object is in motion but with a constant velocity, which is the whole purpose of our experiment. So finally, since the main concept we are analyzing is position is also a very fundamental concept. The equation for position, known as the position update formula, is shown below, and it shows how our position varies with time and velocity, and we use this equation actually to find our different positions with time for both our observation and model. And as can be seen from the equation, our final position is equal to the initial position plus the velocity average times delta t. We'll be using all of these concepts to understand when and why exactly the observation's results are similar or start to deviate from our model's results. Now for the experiment for the tracker part, I first measured the diameter to be 0.066 meters. I placed the calibration stick and I edited the frame to where my ball seems to move with a constant velocity, and this is all represented in the image below. Then I placed the point mass at the center of the ball at variable times, and finally I obtained a time versus position graph. So I was first able to extract the initial time and the final time, which is 0 seconds and 0.46 seconds. And the delta t, I found it to be 0.033 seconds by using the first two values from the chart. The starting vector is 0.00174800 meters. It only has an x component, so it's going in the x direction. And the velocity can also be calculated from the equation at the bottom right of the slide, and it's found to be 0.688500 meters per second. So now I adopted all this information into the code, so we can see that I first edited the ball.m to be representative of my tennis ball mass in kilograms, and you can see that I represented it with a red arrow. Then I placed the initial vector and the velocity to match what I had calculated from my observations, which I just explained. I made the initial t and my delta t as 0 and 0.033, and finally I edited the equations in the second image to the proper equations of the velocity update formula and position update formula, which I already went over. Here are screenshots from my glowscript. Now for the results, here is the graph with the data from my model, which is represented in orange, and the observations in blue. At first glance, we realize that the slope of the orange line, which is our model, is straight, meaning we have a constant velocity throughout, while the observation line slightly changes towards the end to become a bit more curvy. In the first round, 0.1 seconds, we can see that the lines are coinciding, and this is because the F net is equal to 0, and based on Newton's second law, we have a constant velocity motion. So here the model actually forms a good representation of our observation, as their velocities are the same. However, as time increases, we see the two curves no longer coincide, and this is because the F net is no longer 0, and the force of friction acting in the minus x direction becomes greater than the forces from the push of my hand. And thus, velocity is decreasing and the speed becomes slower. This is based on Newton's first law, where since we have an external net force that is acting on the ball, it does not have a constant velocity anymore. However, such results may have been affected by possible sources of error. The main source of error is that the model assumes you have a constant velocity because F net is equal to 0. However, as we just explained, in the real world, the F net is not 0, and thus the velocity isn't constant throughout. And I explained actually more errors on the slide. Now, to answer the questions, what does it mean if we switch the axes? So our positive x is now to the left and the motion remains the same, but the way we describe the values changes. So the slope is now negative and the position values are in increasing negative order. Now, for the second question about the net forces. So the net forces in the x direction includes the force from the push of my hand when I push the ball, acting in the positive x direction, and the force of friction from the floor is acting in the negative x direction. So if the external net force is 0, then the forces remain constant and the motion of the ball does not change. And these are the forces that are acting on the ball to give an F net of 0. In conclusion, it was evident from the data that the final velocity wasn't equal to the initial velocity for our observation. Thus, the F net wasn't 0. So the ball's motion could have been properly represented by the model if we found all the forces acting on the ball and represented them in our model. Thank you.